All right, let's dive right in. We're going to take a journey from the very heart of the atom all the way up to the massive engineering projects that can power our entire world. This is the story of nuclear energy, a force with, well, immense promise, but also some pretty profound challenges. So, to really get our heads around nuclear power, we've got to piece it all together. We'll start with the why, the promise of nuclear energy. Then we're going to shrink way down to the atomic level to see where all that power actually comes from. After that, we'll build a reactor from the ground up and even tour a few different designs. And finally, we'll get to the really big questions. What do we do with all the stuff that's left over? So, yeah, why even bother with nuclear? In a world that is just hungry for clean, reliable energy, nuclear power brings something really compelling to the table, even if it is a bit complex. Let's take a look at why it's such a powerful contender. I mean, think about what this really means for our power grid. A nuclear plant provides what we call baseload power. That's a constant, steady stream of electricity, day or night, rain or shine. And the energy density, it's just astounding. A single tiny pellet of uranium fuel can do the work of tons and tons of coal, and it does it all without the smoke and ash. Okay, to understand where this incredible power comes from, we have to go small. And I mean really, really small. We're going inside the atom itself, to the very heart of matter. So, at the center of everything is the atom. The easiest way to picture it is like a tiny little solar system. You've got a dense nucleus made of protons and neutrons right in the middle, and then you have these much lighter electrons zipping around it. And that nucleus, that tightly packed bundle you see right in the center, that's where the real power is. It's locked away by these immense forces that hold the whole atom together. Now, the key to unlocking that power is a process called nuclear fission. Basically, by firing a neutron at a heavy nucleus, something like uranium-235, we can split it. And when it splits, it releases a huge burst of energy and a few extra neutrons. Those neutrons then fly off and split other nuclei, creating a self-sustaining chain reaction. It's like the ultimate atomic domino effect. Now, an uncontrolled chain reaction, that's a bomb. The absolute genius of a nuclear reactor is its ability to control this process with incredible precision. Engineers are always aiming for this state called criticality, where for every atom that splits, exactly one of the new neutrons causes another split. It's this perfectly balanced, delicate dance happening at the atomic level. Okay, so we've got our controlled chain reaction. Now, how in the world do you build a machine to contain it and actually harness that energy? Let's look at the essential parts of a nuclear reactor. Every reactor needs fuel, something like uranium-235. It also needs a moderator, which slows down the neutrons to just the right speed for fission to happen efficiently. The control rods, well, they act like the brakes, absorbing neutrons to speed up or slow down the reaction. Then you have a coolant to carry away all that intense heat, while a reflector and heavy shielding keep all the neutrons and radiation safely inside. So, with these basic building blocks, engineers have come up with all sorts of ingenious designs. And really, each one is just a different answer to the same question. What's the best way to use fission to boil water? Let's take a quick tour. First up is the boiling water reactor, or BWR, and honestly, the name pretty much tells you exactly what it does. The beauty of the BWR is just how direct it is. The same water that's cooling the reactor core is allowed to boil right there, creating steam that then goes and drives the turbine directly. It's a single, kind of elegant loop from nuclear heat straight to electricity. But what if you wanted to operate at even higher temperatures to get more efficiency? Well, that's where the sodium graphite reactor comes in. Instead of water, it uses a very different kind of coolant, liquid metal. Liquid sodium is just an incredible heat transfer agent. It lets the reactor run much, much hotter than a water-cooled design. To manage all that heat safely, it uses two loops. The first sodium loop gets superheated in the core, and then it transfers its heat to a second loop, which then boils water to make steam. Okay, next up, we have a reactor that sounds like it defies the laws of physics, the fast breeder reactor. Its incredible feature is that it can actually create more fuel than it uses. And no, that's not science fiction. The potential here is just enormous. I mean, think about it. A nearly 100-fold increase in energy yield would mean our current uranium resources could power the entire planet for centuries. It would completely change the global energy picture. So, how on earth does it work? Well, by getting rid of the moderator, it uses high-energy, fast neutrons. These fast neutrons not only keep the chain reaction going, but they also bombard a surrounding blanket of a material like uranium-238, transforming it into brand new, fissionable plutonium-239. It literally breeds new fuel as it runs. All right, our final stop on this tour, the gas-cooled reactor. This design uses an inert gas, something like helium, instead of a liquid to move all the heat around. The big advantage of using a gas like helium is that it can get incredibly hot without ever boiling. This allows a GCR to operate at really high temperatures, which in turn means it can convert heat into electricity very, very efficiently. Some designs are so efficient that the hot gas can just drive a turbine directly. Okay, so with all this incredible power comes an immense responsibility. You have to manage the dangerous byproducts of the nuclear reaction itself. See, the fission process doesn't just create heat, it also creates intense, invisible radiation. To protect the operators and the environment, the heart of the reactor is encased in what's called biological shielding. We're talking several feet of high-density concrete, designed to absorb all those harmful rays.
And that brings us to the final and maybe the greatest engineering challenge of them all. What in the world do we do with the leftover nuclear waste?
This is really the question at the heart of the entire nuclear debate. The fuel gets used up, but its byproducts, they remain dangerously radioactive for millennia. How do you safely manage something that has such a long-lasting and hazardous legacy?
The leading strategy we have right now isn't to destroy the waste, but to isolate it completely from the environment. This means sealing it in these incredibly durable containers and then burying it deep within stable geological formations. And here you can see what that deep geological storage looks like. These waste drums are handled by remote control and placed in these repositories hundreds of meters underground, sealed away in solid rock formations, hopefully for geologic timescales.
So, at the end of the day, we're left with this fundamental balancing act. On one side, you have this incredibly powerful and reliable source of clean energy. But on the other, you have the immense challenge of managing its dangerous byproducts, not just for our lifetime, but for thousands of years to come. This is truly one of the greatest engineering challenges of our time. The future of nuclear power really depends on our ability to innovate, to maximize its incredible benefits while taking full, complete responsibility for its long-term risks. The question is, how will the next generation of engineers rise to that challenge?